In front of you is a current, a transformation, bending every point of space into somewhere new. It looks impossibly complicated, but here's the trick the whole of calculus turns on. Freeze it. Look at one tiny patch. For one instant, drop a perfect little ring of dye on the surface and hold time still. In that frozen patch, the curve has nowhere to hide. Whatever the map does here, it does the simplest thing a map can do. It acts like a straight line. Watch the patch. The point at its center is x. One instant of the flow carries it to f of x. And the ring around it doesn't stay a ring, it tilts. And it stretches into an ellipse. That ellipse is the whole story. Its two axes are the directions the map pulls hardest and least the singular values, sigma 1 and sigma 2. The stretch factors along the map's own axes. And the rule underneath is the gentlest in mathematics. Nudge the center by a small step delta, and the image moves by j times delta. Twice the nudge, twice the move, perfectly linear. That is the Jacobian's defining promise. Near a point, f of x plus delta is approximately f of x plus j delta, the best straight line shadow of a curved map. So a curved map, up close, is just a stretch and a tilt, a matrix. Clean, but that matrix is 4 bare numbers. Where do they come from, and what does each one mean? Line up the input directions. One step along x, one step along y. Send the x step through the map. Where it lands is the first column of the Jacobian j times e1. Send the y step through. Where that lands is the second column j times e2. So every column is just the image of a single unit nudge. Now read the grid the other way. Across a row, and you find something just as familiar. Each row is one output's gradient, the slopes of that one output, in every input direction. 4 numbers, and each has a job. Entry I, j is the partial derivative of fi, with respect to xj, how output I moves when you nudge input j, and nothing else. Now stop asking what the map does to a direction, and ask what it does to a whole region. Funnel the current into a narrows. The water has to go somewhere, and you can watch it darken as it crowds. That darkening is the most useful thing the Jacobian measures. Take a square patch of dye area 1, some density rho. Push it through the map. It comes out smaller, a squashed parallelogram, and the area it shrinks to is exactly the determinant of j, the factor a map scales area by. But look at the dye, not one speck was added or removed. The same count, in less room, so the density climbs, by 1 divided by the absolute value of the determinant of j. Squeeze harder, and it climbs faster. Flip the patch inside out, and the determinant turns negative, that is orientation, reversing. And this is the law that carries the Jacobian far beyond geometry. The density after equals the density before, divided by the absolute value of the determinant of j. It is the change of variables rule, the very same Jacobian, a normalizing flow, uses to turn plain noise into a distribution. But a current can do something a stretch cannot. It can fold, where the water doubles back on itself. 2 places upstream pour into 1 place downstream. Watch what that does to the Jacobian. Mark 2 parcels in the patch A and B. Now drive the smallest stretch towards 0. The ellipse thins and collapses to a line. The determinant falls to 0. The condition number sigma max divided by sigma min. How lopsided the stretch is runs away toward infinity. And A and B land on the very same point. You can no longer tell them apart. The map has stopped being invertible, and that information is simply gone. Here is the ceiling, and it is permanent. The fold is decided by the map. Right here, no downstream step can unmix the 2 parcels. An inverse exists only where the determinant of j is not 0, and the density 1 divided by the determinant races to infinity, which is exactly why a fold line, acoustic, glows bright. A fair warning, though, this linear picture is exact in only one place, the infinitesimal. Stay in a gentle, well-conditioned reach, and it holds far out. The map is trustworthy, but in a wild, sharply curving stretch, the straight line shadow lies almost at once. The Jacobian answers local questions beautifully. Ask it a global one, and the river's own curvature will betray you. So how many different ideas have we secretly been carrying? When the map has just one output, the Jacobian is a single row, and that row is the gradient. Take the gradient's own Jacobian, and you get the Hessian curvature, the slope of the slope. Sit at a fixed point and read the eigenvalues of j. They decide whether a small nudge grows or dies away. That is local stability, the question every dynamical system asks. Stack two maps in series, and their Jacobians multiply. J of G after F equals JG times JF. Push a perturbation forward through the chain, that is J times V. Pull a gradient backward through it V transpose times J, and that backward pass is exactly backpropagation. And that is the one face the river can't draw for you composition lives between maps, not inside a single frozen patch. So we read it straight from the diagram. And the deeper story of that backward sweep, stacked through a whole network, earns a film of its own. 5 threads, 1 river. The local map a stretch and a tilt. In every patch, the stretch itself sigma 1 and sigma 2. The determinant and the density it sets. The fold where the determinant hits 0, and the map forgets, and the many faces it wears. Gradient, Hessian, backprop, stability. One object, running quietly under all of them. That is the Jacobian. Not a wall of partial derivatives, one honest idea. The best straight line shadow of a curving world. Read one tiny instant at a time. Freeze the current, and the whole map is just a stretch. And a twist,